talked about this the last couple of days, mentioned how, we're sort of building the axioms, as I was referring to them, or the rules for adding and subtracting and all those different operations when we're working with vectors, because they're not the same as numbers, the numbers that we're accustomed to. How do we do all these operations with vectors? And adding and subtracting was pretty straightforward. It's kind of intuitive. It uses a lot of skills that we already have. And then multiplying by a scalar, again, was intuitive. But what we said was, well, there's not just one way of multiplying. There are different ways. And they have different purposes. And they have different uses, okay, or applications. And so it's not like when you multiply two vectors, this is what you're doing. It depends on what you're trying to do, which of these three types of multiplication you would use. Okay, so we've already done multiply by a scalar. Today we're doing dot product. Next week we'll talk about the cross product. And the dot product has it has something that it accomplishes that we'll talk about. But for us, I would say mainly, like it has one good use that we will see a fair bit. Okay, so you will be asked to complete the dot product for between two vectors. But then sometimes you might have to realize, oh, I can use the dot product for this. Okay. And when we talk about what the dot product is actually doing, that's not really part of it. That's just for interest and to sort of connect to it and make sense of it. Anyway, I'll talk more about that when we get there. So, when we multiply a vector by a scalar, what do we get? Who remembers? I think this is important to think about because it's really helpful when you're doing something that you know what the answer is going to look like, what it's supposed to look like in case you make a mistake and it doesn't. Or if you're solving a problem and you have a bag of tricks that you can dip into and do things, like if you're doing polynomials, we can factor, we can complete the square, we can do all those things, right? If you don't know what the different operations, what their outcome is, you won't know what you can use when. Like you won't be able to solve problems. So this is important that we know when we multiply a vector by a scalar, what's the outcome? What do we get out of it? It's a vector. Yeah, we get a vector. So let's write that down. And that's just a reminder. Compare that to the dot product. So here's the dot product for vectors A and B. A dot B, we use a little dot, that's why we call it the dot product. When we use a cross product, we use a cross, which looks like the multiplication symbol, like an X. That's where those words come from, but it also means, I hope you understand, you can't change that, right? You wouldn't ever write vector A just beside vector B and assume that's multiplication. You got to say what kind of multiplication, so A dot B or A cross B when we get to the cross product. But notice when I have magnitudes, I can't have them side by side. So the cross product between two vectors is just the magnitude of A times the magnitude of B times the cosine of theta, where theta is the angle between A and B when A and B are tail to tail, not tip to tail, tail to tail. So it doesn't mean two vectors have to be tail to tail. It's like as if they were tail to tail, because you can always move a vector around, right? You can't rotate it or change its size or anything, but if you move where it starts, you'll obviously move where it ends and you're not changing the vector. So this is important. The result of a dot product is a scalar. It doesn't have an output of a vector like scalar multiplication gives you a vector, which is weird because it's called scalar multiplication. And then the dot product the output is a scalar. But what is the dot product? Okay, so let's talk about this a little bit. I think this is interesting and useful. I'm going to write this down. We project one vector. Like if you ever look this up, it would talk a lot about projecting a vector onto another. Onto the other. And then we're kind of multiplying. This is not a rule that you need to know though. So you don't have to memorize this. Multiplying the magnitudes of those vectors, the projection and the other vector. This is not a formal definition. But this diagram, I think, will help us see what's going on. Let's say this is vector B. And vector A looks like this, so I'm going to go tail to tail. I'm going to draw them. What does it mean to project one of them onto the other? Well, it means I would do something like this. I would pull this down at a right angle. And I would figure out, like, what is this length? I'm going to call that C. I'm just going to call it, you could call it vector C, I guess, but I'm just going to call it variable C for now. So what would the length of C be? Remember that theta is the angle between vector A and vector B when they're tail to tail. But that's the projection. Do you see how that's a projection? It's almost like if there's a shadow directly above B at a right angle to B, what part of B would be covered by A? Does that make sense? That's the projection. Okay? How can I find the length of C? Thank you. Cosine is adjacent over hypotenuse. So I've got cos theta is C over A, which means over the magnitude of A. I'm going to make that right because A is a vector, so the magnitude of A would be the number value. So then C equals the magnitude of A times cos theta. So if I wanted to multiply that projection, which is a magnitude, it's a numerical value, by B, I would multiply that. So that, therefore, A dot B, that multiplication of the projection will be A, magnitude of A, times cos theta. Or actually, let me do this. Well, it'd be C times the magnitude of B, right? Which is the magnitude of A cos theta times the magnitude of B. And then I can rearrange that into the formula that we had earlier, magnitude of A times magnitude of B times cosine theta. So it's pretty easy to derive that formula and to understand why it's magnitude of A times magnitude of B times cosine theta. I think that should be fairly straightforward, fairly simple why that works. But why would this be something we would want to do? That's another question. We're going to talk about that briefly. Why would this be something that you would want to do? Like, what's its purpose? Now, I'm going to go out on a limb here and say the why we're about to talk about is not something that's going to come up in this course. But I think it's interesting and I think it's useful for us to connect to these ideas and memorize them a little bit better when we have some of these. So there's three things. I don't think you need to write these down. They'll be on the blog. If you were doing an engineering degree or physics or something like that, then absolutely you would be doing one or some of these. So apparently mechanical work is the dot product of force and displacement vectors. So if they're going at different directions, you would use the dot product to determine the overall mechanical work that's occurring in a particular direction. Magnetic flux is a dot product of magnetic field and the vector area. That one maybe doesn't even really make a whole lot of sense. Like, what's that even talking about? But anyway, there's just another example. And power is the dot product of force and velocity. You recognize a lot of those, and you can, if you've taken physics recently, you would probably be like, okay, that I can kind of see, like, we've kind of done things like that in physics class, so I kind of get that. I have two other good examples, though, that to me are a little bit more easy to connect to. Imagine you have a panel of solar cells, okay? So often you see these panels in fields, and they're actually like they swivel back and forth to follow the sun, right? But imagine you have one and it's fixed. So if the sun's over top of it, okay, the sun has a certain intensity shining down on those panels, and those panels have a certain efficiency. Turns out the overall energy that those panels will produce, or I don't know if it's energy, I might be using the wrong words here, but the analogy or the example makes sense. The energy that those panels will produce will be a multiple of the efficiency of the panels and the intensity of the sun. Does that make sense? I think that makes sense, right? So the efficiency of the panels has to do with what direction they're pointing. That's why they try to have them follow the sun, right? If the sun's shining directly on them, they're more efficient. So if it's like this, the overall energy that they'll produce would be the multiple of the sun's rays times the intensity of the sun's rays, or something like that, times the vector of like the sort of direction of the solar panel. Does that make sense? So the solar panel is going this way, and it's off angle from the sun, so it won't be as efficient, but you could determine that efficiency or that overall energy by using the dot product. That is something that people working in the industry, they would use the dot product for the situation. It is, exactly, and that's something we're going to talk about in the next unit. We talk about planes, and we talk about the way that we describe planes as a perpendicular vector to those. That's exactly right. But this next example is one I like even better, and it's one hopefully lots of you know. Has anybody ever seen this game before? So imagine you're playing Mario Kart, any of the Mario Karts, and you know what this little boost panel does? But if you hit the boost panel going across it, it only boosts you in this direction. It doesn't boost you in the direction you're going. It boosts you in a direction that goes with it. So what would be the boost that you'd get? Would be the dot product. So the programmers of the game would actually have to have your vector of movement and then how it relates to the vector of the boost panel and take the dot product to figure out how much it boosts you in that direction. And you would still be going that direction, but it might throw you a little bit sideways or something like that. But anyway, to me, that's a nice visual, especially if you've played this game. If you haven't played this game, maybe you don't quite follow. But if you played this game, that makes sense. It multiplies your velocity by a certain amount, but by how much has to do with the dot product. Anyway, that's what the dot product is. It has a couple other interesting uses. But we need to know the formula. We'll get to one of the uses in a moment. We're going to do 3 examples of just calculating the dot product. Using it is pretty easy. Remembering the formula when we mix it with some other formulas, and remembering sort of what it does when we mix that with what other things do is maybe the only hard part. Determine each dot product. So we're going to find A dot B, because those are the 2 vectors that were given. So there's our formula. What is the magnitude of A? It's given. What's the magnitude of B? It's given. And the angle between them is given. Calculators in degrees, because the angle is in degrees. And you should get approximately 771.3. What is 30 times 40? 1200. If those vectors were collinear or parallel, and then you thought of them collinear, like if I ran over the boost panel, straight over it going forward, I'm going to get the biggest boost. It's going to directly multiply by my entire velocity. So 30 times 40 would be 1200. That's the biggest boost you're going to get. We're getting part of that, a portion of that, because the projection is not as big. Does that make sense? See how this all works? I hope it's starting to give you a bit of a visual. No units. There could be units if it was centimeters or something like that, I guess, and we might have units, but in this case we don't. Okay, I've got vectors u and v here. So u dot v. Go ahead. What do you notice about these two vectors? Like, what jumps out at you about them? Makes you kind of wonder or just think about what's happening here? Ah, interesting. Yeah. So what do you think? Yeah. And then how does that relate to cosine? Yeah, you can think about it like this is quadrant 2, right? This would be quadrant 1, quadrant 2, quadrant 3, quadrant 4. So quadrant 4 and quadrant 1 would be vectors going in the same direction, positive. Quadrants 2 and 3 would be vectors going in opposite directions, so negative. Anybody done it yet? Did you get the answer? And it works out to, I think, negative 9,899.5, approximately rounded. So it gave us a negative answer. That all kind of fits and makes sense that would happen. One more. All right, somebody tell me something about this one. You guys got that? Got it. What do you think?
90 degrees.
So
Cosine
cosine of
is 0.
90 is 0. That's interesting. So when I multiply through, I get 0. But does that make sense? Why does that make sense? Mary Lou, what did you say? There is no projection, right? It wouldn't. How can we use those examples, or which one of those examples that we talked about could we use to make sense of that? I don't know what would happen in Mario Kart if you ran over it sideways. it might still push you.
Yeah,
Because it's a video game.
Mario Kart, it's actually just the base in whichever direction you're going. I'm not certain.
Apparently it's not, but anyway.
I would be. We should also research it. Yeah. Could we just bring in?
Yeah.
Regular
Yeah. That would be interesting. Actually, that would be fun. Anyway, but okay. What about the other examples that we talked about? Yes. So we're like switching over from positive to negative, and that goes through zero. That's a nice way to think about it. What else? You picture the solar panels? What about them? Useless? If your solar, like if this is the sun, your solar panels like this, they work really well. How well are they going to work if they're like that? None. You're going to get none, right? So to me, that really fits. That really makes sense. Turns out this is really important. So this is something that we really want to remember. The dot product of parallel vectors is 0. If you take the dot product of two vectors and you get 0, what would that mean? Okay, very quickly, some properties of the dot product. Oh, that's the one we were just talking about. So A dot B equals 0 if and only if A is parallel to B. Yeah. Perpendicular. I wrote perpendicular. Why did I say parallel? Thank you, yes, for correcting that. That's the perpendicular side, not parallel. Good? Yeah. When they're perpendicular. If the dot product is 0, they are perpendicular. If they are perpendicular, the dot product will be 0. That's what the if and only if means, and that's a really important thing. Let's take a look at this. A dot B is A magnitude of A times magnitude of B times the cosine of theta, which magnitude of A and magnitude of B are numbers. So can't I reverse those? This is a really complex proof for something that's pretty simple. So what is that? Kind of. So what is this though? It's B dot A. Is what I was looking for, right? If you follow the formula strictly, the first thing in the dot comes first, second thing in the dot product comes second. It's kind of seems obvious, seems trivial maybe, but anyway. So A dot B is equal to B dot A in other words. Now that's a scalar, right? Because the result of the dot product is a scalar. So the value will be the same. And then in terms of what direction you're talking about, like in some cases that may not make sense to talk about direction, but if you're talking about the solar panels or something, projecting one onto the other, maybe it doesn't really even make any sense. But anyway, what about A dot A? Well, let's take a look. If it's A dot A, what can we do?
Cos theta would just be 0, so that would be 1.
It'd be theta would be 0, thank you. So it'd be actually cos of 0. This is similar to what we were talking about if the two vectors were collinear. It'd be the same, except they'd have different magnitudes probably, right? Which means, Jason's exactly right, that's 1. So this is equal to the magnitude of A squared. And I think it's interesting to note that if A and B are collinear. When you take the dot product, you just multiply the magnitudes because the cosine of 0 is 1. So it would just be magnitude of A times magnitude of B, right? If they're collinear. That could be a check if two vectors are collinear. What if you're asked, are these two vectors collinear? I guess if you knew theta, you'd have to know that it was here. Anyway, something that you could possibly use at some point. A dot B plus C turns out is A dot B plus A dot C. So yes, it's distributive. As well as associative. Associative, in this case, with a scalar compared to associative in the other way where the direction of the dot or the order of the dot doesn't matter as well. This is, again, sometimes, okay, so it's associative, fine. But I like to think about this a little bit more deeply where this is a scalar times the dot product of two vectors. What is the dot product of two vectors? The output is a scalar. So this is going to be a number times a number. So if I take the dot product, then I can multiply it by any scalar and just, make it bigger or smaller or whatever. But what's happening here? Well, when I multiply a scalar by a vector, I get a vector. So I'm going to get a new vector here, and then the dot product will give me a scalar. So in both cases, my output's going to be a scalar, but it's going to happen in a different order. So I don't know that it's trivial that it would be associative. You know what I mean? But it turns out it is. It works out the same way, whether you multiply by the scalar first or at the end. Works out the same. Any questions? That's kind of definitional stuff. So using those properties to do some expanding and simplifying, this stuff's pretty easy. There's nothing magic about what we're about to do. It's just an illustration of these properties in action, in reality. It would typically be more like, what are you trying to do? Would you do this or would you do something else? But if I distribute this to both of those, I get K times U dot U. Like I could use that associative idea to do that. Plus K U dot V. So this is K times the magnitude of U squared plus, I can't do much with this one, so I'll leave that. I could change that into the dot product formula, but in this case, there's not really a reason to. And what do you notice about B? Anything? John? Yeah, so what's that? Well, possibly, yes. I think I understand what you're saying. To me, it looks kind of like difference of squares product. So if I expanded this, I'd get U times U, and then U times V, and then negative V times U. So those are going to be 0, then negative V times V, right? So I'm going to get U dot U minus V dot V. The middle terms are going to add to 0. So in this case, I could simplify it very nicely. Any questions about that? Pretty straightforward. Okay, now this last part is important. What about for Cartesian vectors like we were talking about yesterday? Well, let's figure it out. So first of all, I'm going to do this. I'm going to add a vector to this because it's going to be helpful. And I'm going to call it C, and notice the direction that I made it. You could do it in the other direction and it would still work out. You might get, it would still all work out basically the same, but I chose to draw it this way. And I'm going to do a few things to kind of set this up. So what I notice is if I start here and go along B and then along C, that's the same as A. So B plus C equals A. And that means vector C, we've done this before, is A minus B. Vector A minus vector B. And I'm going to define these vectors as AX, AY. We sometimes refer to that as like A1, A2. X and Y can be nice to use because then you remember which one's which. 2 is usually Y, but anyway. And B is the X value of B and the Y value of B. So that means C from yesterday, it might not look like this, but this is simple. If you have Cartesian vectors and you're adding or subtracting them, you just add or subtract the x's and the y's, right? Remember that from yesterday? At least if you don't, you should. That's something that's going to be pretty important. So this is A of x minus the x value of A, minus the x value of B, and then the y value of A minus the y value of B, right? So that's C. Okay? So that's kind of the setup. Now what we're going to do for our next step is cosine law. So if I'm just thinking about the magnitudes of these vectors and I use them with cosine law, I get the magnitude of vector c squared is equal to the magnitude of a squared plus the magnitude of b squared minus 2ab, which are all magnitudes, times the cosine of the angle between them, cosine law from grade 10. And from here, it's just rearranging it into a way that's going to be nice for us. What do you notice about that? Anybody? Like, we're trying to derive the dot product for Cartesian vectors here. So what in that formula so far is useful or stands out? We think that might be useful. Anybody think of anything? The 2? Why does that stand out? Okay. What do you mean by we had A in that spot? Okay. Gotcha. What else? Can you add on to that? Or somebody? I feel like you're implying something but not saying it. Magnitude of A times magnitude of B times cosine of theta. What is that? That's the dot product. So there's a bunch of other junk in here, but the dot product between two vectors is in there as well. So to me, I'm like, well, we probably want to put that on one side by itself, right? That's going to be useful. So let's take that over to the other side, and I get 2. The 2 is in the way, sure, but it's bound to work out, right? Math always does. And then I get a squared plus b squared, magnitude of a squared plus magnitude of b squared minus the magnitude of c squared. So I got to figure out what's going on the right side, and I got to figure out what's going on with that 2. But if I can do all that, I can make all this work out. There's one more thing now that you might realize at this point, oh, I got to go figure this out, okay? And that's going to be the magnitude of a. And do you remember how we found magnitudes of Cartesian vectors yesterday using Pythagorean theorem? Is just a, the x value of a squared plus the y value of a squared. And we could do the same for b and the same for c. I'm not going to write them down here because we're going to write them down again anyway, but that's like from yesterday, right? Because the vector starts with its tail on 0 when those are its coordinates. So it's just Pythagorean formula. All right, now we can do this. So this is equal to the magnitude of a, which we just wrote down in orange over there, squared. So the square root of the x value of a squared plus the y value of a squared, all squared. That's nice, right? What happened there? That's nice. Yeah, the square root and the square are going to cancel. And same thing's going to happen here. So what does this one look like? It's b of x squared plus by squared, all squared, minus, now c is a little bit trickier, because c, the x value of c is ax minus bx squared plus minus by squared. But the square roots are still going to cancel out nicely with the squared. Are we okay with this step? All right, we're going to drop those square roots and we're going to do some expanding. So I've got ax squared plus ay squared plus bx squared plus by squared. Those x's and y's are supposed to be subscripts, right? That one doesn't look like it, but it's supposed to be like small subscript. Minus, I'm going to put a bracket around this. This is one of those silly mistakes that even at this level we still make sometimes. Forget the bracket and you end up getting the wrong signs in the wrong places. Ax minus bx all squared is ax squared minus 2ax bx plus bx squared. Plus, we okay with that? Binomial expansion. That's like a minus b all squared. And they just all have x's on them. Okay. Plus ay squared minus 2ay by plus by all squared. End bracket. And what do we notice? Yeah, and lots of things are going to cancel out. So I'm not even going to bother putting the negative through. I'm just going to say, well, this is ax squared minus ax squared. This is bx all squared minus bx all squared. This is ay squared minus ay squared. And the y value of b squared minus the y value of b squared. So what am I only left with? I'm left with this and this. Now I'm going to distribute the negative through. So this is equal to 2ax bx plus 2ay by And what can I do? Divide out the 2's. What is the dot? What is that saying? Can you interpret that formula now? John? Yeah. How simple is that? If you're talking about Cartesian vectors, for vectors A and B, you multiply the x values of A and B, you multiply the y values of A and B, and you add your two things together. Pretty simple. Kind of nice. So we're going to write this down. If vector A is A1, comma A2, and vector B is B1, comma B2, then A1, B1 plus A2, B2. Any questions? That's a proof you should know. It often finds its way onto the quiz in this unit. Well, the formula you need to know because there will be questions on it, but I'm saying the proof too. Yeah. I know proofs feel long, but by now you've seen a lot of them. This one's pretty straightforward. You might have to remember some of the setup, but then once you've done that, it's like use cosine law, rearrange. This step is like rearrange in a smart way, right? I want this part by itself, and then it's just subbing in and eliminating things. The rest of it more or less falls into place. Okay, let's try to use it a couple of times. So now I'm given the two vectors as Cartesian vectors and asked to find the dot product. It's not harder than it looks. So it's going to be 4 times 5 plus negative 2 times 3. 4 times 5 is 20. Negative 2 times 3 is negative 6. So it's 14. Dot product gives us a scalar. Scalar. Go ahead and do the next one. What'd you get for this one? 0. 6 minus 6 equals 0. What does that mean? The vectors are perpendicular. See how useful that is? So all that stuff about projection and everything is not really something that comes up in this course. Oh, wait, I think that'll work. But that idea right there is absolutely something that comes up in this course. So what were these vectors? 6 and 3. So 6 and 1, 2, 3. I hope I did this so I can actually get them. And then 1 and negative 2. So here's one vector, and here's the other. Sure looks like a right angle to me, but with the dot product, I prove that it is a right angle. Do you remember back in grade 10 when you did analytic geometry, and one of the things that you had to do sometimes is like prove that such and such is a right triangle, and you had to find the slopes by doing like y2 minus y1 over x and all. That would have been easier. Why didn't we teach you the dot product back then? Just to find out if two lines are parallel. Anyway, or perpendicular. Okay. Any questions?